So we are starting with chapter 3. Chapter 3 is about flammable gases and liquids. And so the majority of what we're going to see in this chapter is going to kind of fall into two different areas. We're going to get into a lot of definitions in terms of what does the DOT define as a flammable gas? What does the DOT define as a flammable liquid? How does the NFPA? How does OSHA? Because unfortunately, they can't all agree on things. And there are different standards for transportation versus workplace versus anywhere else. So a lot of this chapter is going to focus on definitions of what it means to be flammable, what it means to be combustible, what it means to be a compressed gas, and so on. And we're going to actually start this by looking at just some general definitions for flammability criteria. So when it comes to flammability criteria, there are generally three measurements that we use to determine if something even burns at all. The first is called the lower explosive or lower flammable unit, or excuse me, limit. We refer to this as LEL most commonly, the lower explosive limit. And this would be the minimum vapor concentration of an explosive or of a flammable in the air that would allow it to ignite. So we can say things like the LEL for ammonia is 16%. And so at 16% ammonia in the air, we know that it can catch on fire. The UEL, the upper explosive limit, would represent the maximum vapor concentration, where we can see something catch on fire. So with LEL, we're talking about what's the minimum. And if we're below the minimum, we're not going to see ignition because there's just too much other stuff in the way to actually sustain any kind of reasonable flame. On the UEL side, we're talking about the maximum concentration. And so above that concentration, there's actually too much fuel vapor that's choking out the ability for the oxidizer, oxygen, to get in there and actually ignite the fuel vapor. And so between those two limits is kind of our sweet spot. And that sweet spot we call either the flammability range or the explosive range. Our range can be calculated by taking the UEL and subtracting from it the LEL. And again, this would be a percent value. So let's say that the UEL is 16% and the LEL is 23%. Well, 23 minus 16, that would be 7%. It would have a flammability range of 7%. So we just take those two values and subtract them from each other. Now, there are other criteria that we can use. These three you might be a little bit more familiar with than the explosive limits. Flashpoint, Firepoint, and Autoignition point. When we describe the flash point of a liquid, what we are talking about is what is the minimum temperature that we need to get enough vapor present to get an ignition to occur. Now, this ignition that is occurring at the flash point is not a sustained fire. It's literally enough to just burn off what's in there and it goes away. So that's why it's called a flash point, because out of the flash point, we literally see a flash of fire and then it extinguishes itself. We're more familiar with the concept of Firepoint. Firepoint is just what temperature do we need to get a controlled burn of the substance. So I take gasoline, I expose it to flame, the gasoline catches on fire. We know that we are at the minimum at the fire point of the gasoline. So the difference between Flashpoint and Firepoint is sustainability. Again, the Flashpoint is just that. It is a flash. It's a flash in the pan. It ignites, it goes out, all within microseconds of each other. Firepoint, it lights, it stays lit. But I need to introduce a match or a flame or something to it to get it to light. Striker, flint, something, spark. Auto ignition point is the third. And then the third one here, we don't even need the spark or the fire or the flame or the flint or the striker. At that temperature, it ignites on its own. Not every liquid is capable of doing this. And as you might expect, if we are to compare the three temperatures to each other, each one is going to be successively higher. The flash point of a liquid is going to be lower in temperature than its fire point. The fire point is going to be lower in temperature than its auto ignition point, if it has one. Now, if you go into most reference texts, you'll find Flashpoint as kind of the listed measurement for flammability for a substance. But the other two do exist, especially for materials that we know to have relatively low flammable points or relatively high volatility kinds of issues. The way that we test is using something called the Penske martens test. In this test, you end up taking a cup filled with your liquid fuel. You gently warm it up, and every degree or so, you bring a pilot flame into the airspace above that liquid fuel to try to get it to flash, to try to get it to ignite. And when you see that flash, then you can record that temperature as the flash point of the substance. So let's get into some of those definitions. So now that we kind of can compare flash point versus fire point versus auto ignition, let's look at some definitions of comparison. So OSHA defines a flammable liquid as any liquid that has a vapor pressure that does not exceed 40 psi at 100 Fahrenheit and has a flash point at or below 200 or 199.4 degrees Fahrenheit. Now, why these two criteria in particular? Well, this one here, this is what they are using to define it as a liquid. If it has a vapor pressure greater than that at that temperature, OSHA classifies it as a flammable gas instead of a flammable liquid. This bottom criteria, this is what OSHA is defining as the threshold of flammability. So it is possible to have flash points greater than 200 Fahrenheit. But if that flammable liquid does have a flash point greater than 200 Fahrenheit, OSHA doesn't consider it to be flammable. And the primary reason is you're getting up near the boiling point of water there. If you are in an atmosphere that has that kind of condition, there are usually other things going on that are of a much more pressing concern. And so you would obviously deal with those hazards first, rather than worrying about whether or not that liquid's going to ignite. Now, OSHA breaks apart its flammability criteria into 4 categories. And the category that each liquid goes into depends upon 2 things. It depends on the flash point of the substance and the boiling point of that substance. So this is different than the flammability criteria that we saw with the NFPA. Remember, the NFPA placard system said that a category 4 was the most dangerous, and that category 0 was the least dangerous. This is the opposite. OSHA wraps things in a different order. Category 1, these are the most dangerous flammable liquids. And we know that because in category 1, and actually in category 2, we are defining the flash point at less than 73.4 degrees Fahrenheit. Now, can any of you tell me what is significant about 73.4 degrees Fahrenheit? It seems very specific, but 73.4 degrees Fahrenheit is what OSHA is defining as room temperature. So in order to be a category 1 or category 2 flammable liquid, you're talking about a substance with a flash point that is less than room temperature. That's the significance of that particular temperature. And again, why they chose 73.4 degrees, I couldn't possibly tell you. But that particular criteria of being below it is indicating that we are talking about a substance that is going to ignite, even partially, at temperatures lower than room temperature, which should give you an idea of how serious we consider their flammability. Now, the difference between category 1 and category 2 is that boiling point. Boiling point for category 1 is going to be at or below 95 Fahrenheit. For category 2, it's going to be anything above 95 Fahrenheit. Again, Why that particular value, I'm not certain. 95 Fahrenheit, the only thing I could think of just off the top of my head is that you're talking about, you know, a pretty hot summer day versus a not that way. But even at that, that's pretty lousy conjecture. For categories 3 and 4, we're going to see that we are above Flashpoint values. So notice that in categories 3 and 4, nothing is being said about boiling point at all. It is just based upon Flashpoint. So if the Flashpoint is between room temperature and 140 Fahrenheit, it is considered a category 3 flammable. If it is above 140 but below 199, we consider it category 4. And again, above 199, we don't consider it flammable, at least not according to OSHA. So those are the OSHA categories for flammability. Now let's compare them to the NFPA, because again, both are kind of coming at it from the same direction. OSHA from Occupational Health and Safety, NFPA, that being the National Fire Protection Act. Where are the differences between the two? Now, for the NFPA, there are two definitions. Again, you would think it would make a little sense that there'd be a little more common ground. And if you look close, there's some. But there is a distinction made by the NFPA here. A flammable liquid, by NFPA standards, has to have a flash point below 100 Fahrenheit and a boiling point also below 100 Fahrenheit. That's what it means to be flammable according to NFPA. If something is determined to be combustible, so this is a subcategory, then we're talking about a liquid that has a flash point at or above 100. And so what we'll see here in a second is how do these criteria fit into those red diamond placards that we associate with the NFPA. So again, prevailing difference, flash point. 100 degrees is the target line. Below 100, we consider it flammable. Above 100, we consider it to be combustible. Now, just because it's combustible doesn't mean that it's still not dangerous. Now, the NFPA, like the DOT, or excuse me, like OSHA, does separate their flammables into categories. And we'll start with the first three categories, class 1A, 1B, 1C. All of these describe flammable liquids. In class 1A, we're talking about a flash point below 73. That sounds familiar. And a boiling point below 100. Also should sound familiar to you. This is the exact same definition that we gave for category 1 in OSHA. Class 1B, Flashpoint below 73, boiling point above 100. Again, this should sound familiar. This is basically the same definition as the category 2 in OSHA. Class 1C for NFPA, we have a flash point at or above 73, but below 100. And then for class 2, we have a flash point at or above 100, but below 140. And they're at, and NFPA adds one other set of conditions. If there is a liquid mixture where more than 99% of its components have flash points at or greater than 200. So this first part defines if I have a pure substance so if I were looking at straight up isopropyl alcohol, I would define it as class 2 if isopropyl alcohol fit into that window of flash point. But what if I have a mixture of isopropyl alcohol and benzene and a whole bunch of other stuff? Well, if that mixture and 99% of its volume or more had flash points that were greater than 200 Fahrenheit, which that mixture I gave you would not fit into this category. All those flash points are well below 200. But if I had a mixture of combustible liquids together, their collective flash point would actually put it into this range. And so this bottom part here represents if I have mixtures of combustible substances. If I have a mixture of combustible substances, it'll fall into this category because collectively their fire hazard is going to be greater. There are two other categories, and again, they're based solely on flash point. Class 3A, we're talking about flash points for a liquid above 140 but less than 200. And class 3B, we're talking about substances with flash points above 200 Fahrenheit. And notice also, when we went from the class 1s to the class 2 and class 3, notice how our description changed. We went from calling them flammable liquids in class 1 to combustible liquids in classes 2 and 3. So you can see, even in the language, that's where that defining line is between the two categories. Now, how do these map to the NFPA placard, that red diamond side of the 4-diamond placard? Well, as you know from chapter 1, you can have a designation of 0 to 4 in these quadrants. Where 4 or 0 is basically not flammable, and 4 is extremely flammable, and the other 3 kind of vary in shades of gray between the two. So we learned all this in chapter 1 already. Now, how do these criteria that we just talked about map to this? Well, here's how it goes. If something is classified as category or as class 4, so it gets a rating of 4 in the NFPA diamond, we're talking about those gases and liquids that have flash points below 73 and boiling points below 100. So again, we've mapped this already. We're talking about your category 1 OSHA, your category 1A NFPA flammable liquids. Group the rating of 3. Now we're talking about gases and liquids that still flash points are below room temperature. Boiling point is at or above 100. Or we're talking about liquids that have flash points in that secondary range between 73 and 100 Fahrenheit. And so if we go back, that covers the 1B and 1C in that category 3, or that rating number 3. The number 2 is designated for flash points at or above 100, but below 200, or for solids that readily give off flammable vapors. So notice, as we go from 3 to 2, we take out the mention of gases. If a gas is flammable, it automatically goes up to 3 or 4 just from that. Because again, its boiling point would have to be on the lower side for it to be a gas, which means it's already kind of dangerous in that regard. So if it's flammable and gaseous, put it in 3 or 4 automatically, depending upon where it is. In category 2, we're only talking about liquids. We're talking about liquids in that 100 to 200 range. And so, again, if we look back, that would cover anything up to 3A. In rating number 1, we're talking about liquids or solids or semi-solids that have flash points at or above 200. In our designations for liquids, that would be class 3B. But it would also include some solids and other materials that do give off vapor as they decompose. And then finally, class 0, you already knew this. These are materials that do not burn and would include materials that would not burn in air when exposed to a temperature of 1500 Fahrenheit for up to 5 minutes. So basically the criteria there is if it's not going to burn at 1500 Fahrenheit, it ain't never going to burn. And so it gets a category 0 as a result. If it does burn at those conditions in that test, then we move it up 1 line. Because basically the only time we're going to see 1500 Fahrenheit in a normal circumstance is in the event of a fire. I mean, I guess there's some exceptions to that. If you're talking about, melting steel or, those kinds of metal work processes, you can get temperatures up and above 1500. But in your general ordinary circumstance, if you're welding with an acetylene torch, chances are pretty good you're not going to have other flammable materials around you at the same time. It's kind of a recipe for disaster. All right, any questions about these flammability criteria and the NFPA? All right, so I'm going to roll it back here just for a second here, talk about the DOT. Department of Transportation also defines a flammable and a combustible liquid. For flammable liquids, we're talking about any liquid having a flash point of not greater than 140 Fahrenheit. Where there is a difference, so obviously that temperature standard is higher for transport than it is for workplace. One of the main reasons why transport, you're going to be out in rougher conditions generally than you would in a normal workplace. You've got the sun beating down on you. You've got in summer-like conditions. You've got heat coming off of the asphalt that's going to naturally warm up the engine. You got a whole bunch of other stuff going on there. 140 is the reason, is raising that bar just because 100 degree or a 73 degree criteria just isn't practical. We can also define flammable liquids in a DOT as materials in the liquid phase with a flash point at or above 100 that are intentionally heated for transport, or they are transported at above their flash point in bulk packaging. Where we tend to see this most often are things like rail cars, where the rail cars are heated through some sort of tank system to keep the substance molten or at a more transportable, more agreeable kind of state of matter. So usually, again, we see this with solids to keep them from gelling up. We see it with liquids as well to keep them from freezing in certain conditions. So they get warmed up so that they stay in the liquid phase so that when they get to where they're going, they can be easily moved from the car to wherever, as opposed to finding that it's full of ice or jelly or something like that, and it's a pain in the tail to clean up. So DOT, slightly different definitions because of the more difficult kinds of situations associated with transport. And for that reason, combustible liquids kind of follow into the same idea. But this is really important. One thing that is mentioned here, any liquid that does not meet the definition of any other DOT hazard class and has as a flash point between 141 and 200. So 200 degrees Fahrenheit is still kind of the standard we use to determine between combustibility and non-combustibility. That's been consistent through all three of the systems. But note here, why does the DOT make this particular determination? Because if there are other hazards at play, they're going to be much more dangerous and much more noticed than the combustibility. So if this particular substance is toxic, the placard's going to be black and white for toxicity, not red for combustibility. Now, maybe it has both placards on it, but we're going to obviously tackle the much more dangerous aspect of it and worry about its combustibility later. So just a couple of final things before we call it a day today. Empty containers. Now, it is generally not good practice, especially when we are dealing with gas tanks of any kind, liquid tanks of any kind, to presume that when it's empty, it's safe. Anytime we're dealing with liquids, we know that we have to deal with vapor pressure. And so regardless of what is in the container, we have to understand that that container, even when we empty it of all of its liquid, is still going to have some vapor-driven substance in it still. So if the substance inside of the tank happened to be flammable, then we know that the vapor inside is also flammable. If the substance inside happened to be toxic, then we know that there is toxic vapor still inside of that tank. And so we have to be careful about its release. We have to be careful about its being discarded. So when it comes to empty containers, you've got to be careful about just cutting into them or welding into them without any kind of thought about it. You cut into a tank that was holding a flammable liquid, and now you're exposing that flammable liquid to your acetylene torch. And guess what? You've got a bomb. Because the vapor inside is all trapped. It's going to ignite very, very quickly. And when things ignite, they create tons of gas, and tons of gas contained in a small space is a bomb. You don't want to do that. So make sure that you are dealing with things cautiously. And remember that no tank is ever truly empty. It just means that all the liquid's gone. Still got to handle the part of emptying the vapor out before you do anything else to it. And then finally, accelerants. Accelerants are not in any of those hazard classes that we talked about, but generally speaking, accelerants are flammable substances, either in the solid, liquid, or gas phase. And what they are used to do is be basically fire starters. They can initiate the fire, they can promote its spread, and generally speaking, they can make it happen way faster than anything would be otherwise expected to do. Now, on the firefighting side, on the crime scene analysis side, accelerants usually leave a marker, a chemical marker, somewhere to let you know that they are there. And those chemical markers can actually be used to help us to identify arsonists, because usually arsonists leave some kind of a calling card or tend to do things the same way each time. So that's where we will stop for today. And on Wednesday, we'll get into compressed gases, and we'll talk a bit about some of the hazards of compressed gases just themselves, as well as proper methods for storing and transporting those gas cylinders. Have a good day.